All right, if you are watching this video, hopefully you have already done integration by parts and you've done these 4 problems for integration by parts. This video is going to expect that you already know how integration by parts works and you know that it uses, I'm going to scroll back, this formula right here, right? Integral of u dv equals uv minus the integral of v du. This video is covering some special cases of integration by parts. It's going to cover 2 things: repeated use of integration by parts and something called looping. First off, repeated use. All right, if I wanted to find this integral of x squared e to the x dx, this is another integration by parts problem. It's got these 2 parts being multiplied. I don't know how to do it with u substitution or anything else, so we can try integration by parts. From the last video and the last homework, you should understand that the whole goal is picking a good u that eventually disappears. And if for this one, if my choices for u was e to the x or x squared, I would definitely pick x squared for my u, because the derivative of x squared is 2x, which is at least a little simpler than x squared, right? Derivative of e to the x is e to the x. It's never going to go away. Derivative of x squared is 2x dx. So I'm like, well, that's at least getting better, right? So then if my dv was e to the x, my v would be e to the x, and I could use that integration by parts formula and just start seeing where it takes me. In this case, integral of u dv, well, I chose u to be x squared, dv to be e to the x dx, so that's all of it here, right? So that ends up being this part. So the integral of x squared e to the x dx, exactly what I'm looking for, ends up equaling u times v, so x squared times e to the x, right there, minus the integral of v to u. So minus the integral of v, which is e to the x dx, right there, times du. Du was, v was just e to the x, right there, times du. Du is 2x dx. I split it up. I put my 2x in front and the dx out there because I like having my 2x first. Big deal. Normally, then we would just find this antiderivative and we'd be done. But the problem is we look at this and we're like, oh, wait, that's 2x times e to the x. I don't know how to do that with anything else except for, guess what? Integration by parts again. So we just do integration by parts again. Look at this equation, pick a u, pick a dv, and do it again. In this case, we're going to do integration by parts again, but this time, which one of these 2 things do you suppose u should be? That's right, I'm hoping 2x. So we're going to have u be 2x, which means all the rest of this junk, e to the x dx, that's going to be my dv. Since I've got a u, I'm going to need to have the du. Well, derivative of 2x is just 2, so du is 2 dx. Since I've got a dv here, I'm going to need the v, the antiderivative, but antiderivative of e to the x is easy. It's just e to the x. So we do this thing again. So this integral that I'm looking for is going to equal this stuff minus that stuff, which is going to require integration by parts. So writing it out, here's that stuff just copied down here, minus integration by parts says uv, so uv, right there, 2x e to the x, minus the integral of v to u, so minus the integral of v e to the x, right there, du. Du is 2 dx. There's my 2, there's my dx. I look at this thing and like, oh, well, that's an integral I can find. Typically, oh, one thing I should watch out for. You'll notice how I put these parentheses in here. I was subtracting this entire integral. So when I did integration by parts, I'm subtracting that entire integration by parts formula, right? A lot of people, when they do this, they'll write parentheses first, and then they'll say, well, those parentheses are annoying, so they'll take care of that first. I believe that's what I did here. Yep, totally. Minusing that right there. Minusing a negative is like adding. And then I perform the integral. Antiderivative of 2 e to the x is still 2 e to the x. So my final answer, x squared e to the x minus 2x e to the x plus antiderivative of 2 e to the x was still 2 e to the x, 2e to the x. Of course, plus some c. All there is to it. So integration by parts, sometimes you have to do it repeated. Sometimes you have to do it again. So if I had an x squared here, I'm going to have to do it twice, once to get it down to 2x, and then again to get it down to 2. If this is an x cubed, integration by parts would totally work. I would just have to do it, that's right, 3 times. Just repeated use of integration by parts. All right, there's also an example called looping. And this one's going to be the weird one, but I find it the coolest. If I wanted to find this integral, e to the x times cosine of x dx, if I asked you to find your u, you might be like, I've got a problem because it's not like this one before. We're picking u being x squared will eventually make that u go away, right? Derivative, derivative, derivative. Eventually you can get that x to go away. Taking the derivative of these ones, derivative of the e to the x is always going to be e to the x. Taking derivative of cosine, well, it's going to go down to negative sine, and then derivative of that would be negative cosine, and the derivative of that would be sine. And I just keep looping and back down the line. So it really doesn't matter which one you pick. For this problem, I think I picked, yeah, u was cosine, dv was e to the x. I forgot my dx. There should be a dx right there. E to the x dx. I just picked those randomly. I think I picked ub cosine because I prefer taking the derivative of trig functions instead of the antiderivative. All there is to it. Since I've got a u, I need a du, which would be negative sine of x. Since I've got a dv, I'm going to need the v. The antiderivative is e to the x. And if I plug it into the formula, I end up with this thing. Let's double check it. So this was my u dv, cosine of x. There's my dv, e to the x dx. That equals u times v, cosine of x e to the x, right there, minus the integral of v du, so minus the integral of v e to the x, times du is negative sine of x dx. There it is right there. I find this annoying, being e to the x times a negative sine of x, so I'm betting the first thing I did was, yep, distribute the negative. Negative times a negative is a positive. And then I looked at this thing, I said, well, I don't know how to do that, so guess what that's going to require? Sorry. That's going to require integration by parts again. This time I had u be sine of x, again, because I like the derivative there. dv was e to the x dx again. Do the same type of works. Derivative of sine is cosine. Antiderivative e to the x is e to the x. I've got all my u's and dv's, and I do this whole formula again. This stuff is already there, stays the same. Integration of this thing would be uv. So sine, e to the x sine of x, right? E to the x sine of x, u and v, minus the integral of v to u, minus the integral of v du. V is e to the x, so e to the x. Du would be right here, cosine of x dx, right there. So I end up right back where I started with. Remember, that's what I was trying to look for in the beginning. I end up back there, and at this point, I'm like, why am I going to keep doing integration by parts? I just keep going. It's never going to go away. However, this is kind of an interesting thing that happened. I ended up at the exact same place I started up with. Like, this is the integral I'm looking for, and that's what showed out again. I'm trying to find that same integral. I'm going to take this equation. I'm just going to rewrite it as a single line. So I know, based on what I've done, integration by parts twice, that the integral of e to the x cosine of x dx is going to equal this stuff minus the integral of e to the x cosine of x dx, minus the same stuff. Well, this is an equation that we know is true. That and that are the same. I can move this over to that side, right? Add the integral of e to the x cosine of x to both sides. We end up with 2 of these integrals. It's just equal to that stuff. Well, if 2 of these integrals equals all of this, e to the x cosine of x plus e to the x sine of x, that means one of the integrals is going to equal half that stuff, which means I found my answer. I find it really cool. So looping is a weird one where when you take these derivatives, you end up just kind of coming back to where you started. You looped back to where you started. And when you do that, you can rewrite the equation as a whole. Then you say, well, this equation, that integral is over here, it's over there. You can add this integral to both sides. You end up with 2 of those integrals equal to something that you know. And if 2 of the integrals equal something that you know, one of the integrals is going to equal half of that something. And again, don't forget that plus c. The looping example, it's the easiest to forget that you have to have a plus a constant at the end. So there it is. That's the answer. The integral of e to the x cosine of x dx is 1/2 e to the x cosine of x plus e to the x sine of x plus some constant. If ever you're not sure, you could always take the derivative, but I promise you, if you take the derivative of this, you're going to end up with that. That's all it is, short and sweet. You have 1, 2, 3, 4, 5, 6 problems to practice this. I believe the first 2 are going to be on something like this, where you have repeated use of the integration by parts formula. And the second couple, you're going to do a looping example, which is kind of repeated use, right? We still did the integration by parts formula a couple of times. I want to see if I can bring it up. Forget it. You did an integration by parts formula a couple of times, but in that case, you ended up looping back to where you began. Give them a try. Good luck. See you later.